Okay, and now to the southeast end of the county, to the M38 bridge over the Sturgeon River.
Hello, we are the Pier Protectors, and we were studying debris mitigation devices for in front of the M38 bridge on the Sturgeon River. I'm Madison.
I'm Kelly.
I'm Carla.
I'm Scott.
So the objective of this class, that's already been covered by the other two groups, was to really start to prepare us for our jobs as engineers after we graduate. So we had to start by empathizing with our community, trying to find problems that may affect them the most. So we originally were directed towards the Father's Day flood. Everyone in our class kind of started there. And we were thinking, well, what are some other large flood events that could happen? And then we started studying Cricket Dam, where there might be a potential failure someday. We defined our problem a little bit more though, and after consulting with the dam supervisor, we decided to study a little bit more towards the flooding possibilities for any large storms or a dam failure. So we moved towards studying debris mitigation on the M38 bridge. We ideated a little bit and we came up with several different solutions, such as sweepers and debris deflectors as our devices. And then we had to prototype and test them extensively. So we built our own model of the river. And we were hired by Chris. So we consulted with him because he is the Houghton County Emergency Planning Manager, as well as Dave Tripp from the Cricket Dam, to sort of find a starting point and find what these potential flood possibilities could be. So the main pain point we're looking into is any high flow event, which could consider a dam failure, or we're starting to look towards storms as they're happening more frequently. So the Sturgeon River and surrounding communities are very rural and isolated. There aren't very many transportation options. It's pretty much just 38 as the main roadway. And if anything were to happen to that, people will need to direct about an hour out of their way to get around. And it is very difficult for emergency vehicles to have to deal with this because it will increase their response times so much. So we're really looking into protecting drivers and residents who live along this river, many communities downstream. So this red dot is right at our bridge, and a little bit north of it is the Cricket Dam. And then, as you can see from the arrow, flow will continue down towards Chassel. So we really want to try to prevent any large flooding that's happening around 38 or along the bridge. So this is our bridge we were studying. The U.S. Forest Service in a 1998 report said that scour was the single most common cause of highway bridge failure in the United States. So you may be thinking, what even is scour? Well, as you can see in the top image, scour is when water creates vortexes that start to dig up the sand and erode it, mostly around bridge piers and other structures in the water. Scour critical is what our bridge has been defined as, which means even though there is not currently any scour happening, there is great potential for it, especially as large flow events continue to happen. So we need to protect the bridge from scouring. We learned from Dave Tripp of Cricket Dam that the water or the flow levels from a dam failure are predicted. We know all of the information about what the levels will be, when they will hit each specific point along the river, but we don't know anything about what will happen in a rainstorm or what will happen with debris from either the dam or a rainstorm. We really needed to understand more about this. We also want to reduce the effects of debris buildup, because as this debris builds up, it will increase the randomness of the scour patterns, and we won't be able to predict what's happening until it's already too late and there's failure starting to occur. This is an example of what scouring can do to a bridge. It took out a bridge pier right in the middle, which then brought down the entire deck.
So for our project, we decided to look at two different debris mitigation devices, debris deflectors and debris sweepers. So quite simply, debris deflectors are a large sunken post into the riverbed. It is designed to either catch large debris from piling up on the bridge pier, or help rotate smaller and medium-sized debris that bump into it, and help it rotate for its flow to be more linear with the stream itself. This debris mitigation device works best when the flow of the river is directly linear towards both the deflector and the bridge pier. And it has a lower cost of installation as well as lower cost of maintenance. It has received very good reviews from state departments that have decided to implement it into their debris mitigation. The second device that we decided to look at were debris sweepers. Sweepers are devices that rotate on a vertical axis. What it does is it helps debris that bump into it sweep it under the bridge itself. Just like the debris deflectors, it works best when flow is linear both towards the sweepers and the bridge piers. It is also very unintrusive towards recreational activities such as boating. It has a cost of around $50,000 for installation and product, but it has been known to fail under high lateral stress from debris as well as the many moving parts it contains.
So when we conducted our research, we, as Carlin mentioned, found a lot of qualitative evidence for how the states that implemented these devices rated them on a scale from poor to great, but relatively low or few quantitative data that we could base our recommendation off of. So we decided to conduct our own experiment. And in a nutshell, that experiment, we found bought 5 standard gutters, cut 3 of them, and glued them and taped them together to get them to be relatively waterproof. Then we taped the ends together so we could achieve a adequate water height, and added sand and altered the flow rate until clear water scour was achieved, which the diagram on the bottom left shows. And this is our model design in the Water Resources Lab. So the scouring was measured by taking the height before, at, and after the pier, before and after the test occurred. The scale for the river from Google Maps, which is variable because of the seasonal changes, was around 100 feet wide, and the distance between the piers was 70 feet. And because our scale was only 8 inches, the margins were pretty narrow. So doing a full river width experiment was going to be much less representative of what the actual river would look like. So we chose to do a half river experiment, only representing 1 pier in the river. For the debris mitigation, we measured that by sending counted and known handfuls of debris, as you can see by the pictures above, down the river, and counted the amount that accumulated on the pier or mitigation device. As you can see, we have all sorts of ranges, ranging in diameter versus length, so we could get a representative example of what the mitigation devices or pier could see in a large flow event, and including waterlogged or water content and softness and hardness. So, in order from left to right, we have the control, which is a Gorilla Glue bottle. You can probably see it. We chose that to reduce the amount of time we spent constructing the experiment, and it's remarkably similar to the shape of a bridge pier. From left to right, so we have the control, we have the deflectors, which is just a post, and the sweepers, which we 3D printed a gear-like, and then we put a bearing on it and put a post around it too. And the top row is before the test occurred, so there's no obvious scouring occurring, and there's no scour lines. And then after the test is the bottom row, which the red lines are outlining the closest scouring that was occurring at the devices. As you can see, the scour lines for the deflectors and the sweepers are altered compared to the control. And this is for many reasons. Our best guess is due to the positioning of the mitigation devices. Their scour piles, which is when the scouring is pulled up in front of from the front of the pier, it's deposited behind the pier. And those scour piles were put in front of the actual pier itself. So therefore still reducing scouring at the pier and helping us with our our test. And we'll see some video. And here you can actually see the scour lines occurring, and this is what the device would look like full scale. That's great, yeah. And this is a video of the deflector. So as you can see, this is performing just as predicted as the papers that we found said, where some of the debris would get trapped on the deflector itself instead of getting trapped on pier, and some of it is hitting and bouncing off. So as with any scaled down experiment, we had problems. In actuality, the sweepers were supposed to be rotating with the flow of water, which because of how small our experiment was, the sweepers just didn't have enough surface area and the flow wasn't high enough that the sweepers would actually just rotate with water. They would only rotate once debris would hit it. Model deflectors that we used compared to the ones that we designed are a lot bigger than what they would be in actuality. And this is due to the fact that the way we had to attach the deflector to the gutter was under compression with some tape. And when we used smaller diameter dowels, they broke. So we had to resort to the bigger ones. And finally, one of the last problems we came up upon was for the debris mitigation results, our experiment was not conclusive. So we are going to be relying on other information for that part of our recommendation.
So these are our lab results. As you can see, we measured the sand height at the front of the pier, at the center of the pier, and at the end of the pier. For each test, we started at a sand height of around ½ inch. And you can see that scouring occurred more severely at the front of the pier after each test. You can see that the two mitigation devices reduced scour considerably compared to the control test. And looking at it more closely, we can see that the debris deflectors were better than the control tests, while the sweepers performed the best out of the three. However, we did notice this phenomenon while we were testing, that there were scour piles forming at the behind each mitigation device, and that may be because that may be why we see that the sand height for the end of the deflector test and the sweeper test is higher than the control end. Ultimately, scouring is a very complex and unpredictable event and phenomenon, and so it is hard for us to determine exactly why the test showed more favorable results for the mitigation devices. So because of that, we have to look at external sources to help us become more informed about which device might work best. And so since our tests were not indicative of any debris mitigation device, we decided to look at a paper from Kim et al. Out of South Korea. And their test was a lot more thorough in terms of different variables such as flow rate, flow height, and testing different mitigation devices. You can see their results on the right side of the screen. A lower accumulation rate is better, and so you can see that the debris deflectors worked phenomenal, as well as the sweeper. But we can also see that debris did accumulate at a much higher rate for the control test, and this led us to a recommendation.
So although sweepers performed better at the actual act of removing and changing the direction of the debris that was flowing, they do contain more mechanical parts, which means in addition to the normal maintenance that would occur after a storm of somebody going out and removing debris, they also require regular maintenance to ensure that they're still spinning and floating properly within the river. For this reason, we chose deflectors as our recommendation. Because they don't have any mechanical parts, so they only have to be cleared after storm events. And they also have a cheaper initial cost because they are much less complex to build and install. They're also a lot more personalizable to each location. For any river, not just this specific one, you can do a study on it and determine where exactly the deflectors need to be placed. And then you can change the orientation of them. Whereas with sweepers, they have to be fixed right in front of the pier, so they aren't as effective in as many locations. More testing will be needed after this, but we can provide a general idea of where deflectors could be placed in a river, such as right in front of the pier. Or they are normally in larger flow rivers, are placed in a V direction, so that the V is facing upstream, and it will push debris out and away and break up any large bumps.
Alright, so we did do a preliminary design, mostly for budgeting concerns. This is the loading that was considered, so there's only two types of loading for it, and basically cantilever being taken out of the river. And so you have to worry about debris and of course the flow from the water hitting it. And for the debris, we considered a very large pine tree, 80-foot tall white pine. And for the water flow, and we calculated the input back force, we also needed to use the water flow. We already had information from the Cricket Dam failure because OPCO provided us with the inundation maps. So I used their volumetric flow rate to help me calculate velocity, where I took a topographic map and a cross section of the area and had a rough estimate of the cross sectional area. So we came up with a velocity of about 10.7 feet per second, which is like 7 miles per hour. And the other thing to consider is the height of the deflector. So if the dam fails, the water can actually go over top the bridge. We're not going to design for that because it's a cantilever beam, and that large tree creates a huge moment the higher up it is. So the lower you make the deflector, the less you have to worry about that moment. And normal flow rates are not going to be anywhere near the top of the bridge. And next slide. So this is not the data from our specific location, it's data from upstream a bit where there's a monitoring station, and it's the gauge height of the river there. And it never tops 12 feet. Obviously, this isn't our location, but it's indicative of what the normal flow is. And I didn't want to go down to 12 feet because I don't know what it's like at my place, our location. So I went with 15 feet as a design consideration. And next. And so at 15 feet, I did need to add reinforcement to the deflector. So typically, at least from what I was reading, these little deflectors don't have reinforcement in them. So I'm a bit worried that I overbuilt it. But so I put reinforcement in it. There's number 11 bars, and the round HSX section is a 20-inch diameter with half-inch thick steel. And then for the foundation design, we used a rule of thumb to pull, so it's 10% of the pole length, and then an additional 2 feet, so we got 3.5 feet, and that'll probably have to be adjusted with soil data when it comes in. The last thing I want to mention is you can, if you want to design slightly lower, get away without reinforcement. So like 11 feet, you don't even need reinforcement, but that would need more data on what the typical height of the river is. Of course, I'm also not too concerned if you do make it shorter because it won't fall over. It'll just be in that one case where it does overtop the deflector. Well, you didn't block debris that time, but in most cases it was still covered. So it's not too much of a concern if you don't fully quite as high.
So as you saw before with the foundation, we will be changing the riverbed, and that requires us to get a permit. And that permit would be a joint permit from Eagle and U.S. Army Corps of Engineers, complying with Part 303 of the Wetlands Protection of the Natural Resource and Environmental Protection Act. So for a cost estimate, we use the book provided by the CEGE department, the heavy construction cost with RS means data. And we got around a total cost of around $18,000 for 5 days of construction, including all of 40% overhead, since we didn't know soil types, equipment rentals, labor, and everything that is all the materials that are needed for the actual deflectors. Thank you for your patience and listening. And are there any questions? Are there any Zoom questions?
Potential concerns of deflectors being knocked over and causing more damage, like if they were to be bent, say 45 degrees over by debris, how does that impact the scour ability of the debris, or increase or decrease or indifferent?
Well, so we only considered what would happen if it got completely uprooted, and the weight that the deflector would be would not be enough to be taken even in the worst case scenario, which is the dam failure. So that's what we considered for exacerbating issues. A 45-degree, it depends on the river height, I think, for that, because if it was above it, it would do nothing, obviously, but if it was below it, it would still act as a deflector.
It's just a general question. In your literature search, did you come across anything about trying to keep debris out of the stream? Any like forestry management practices or?
Do not believe so. We did quite extensive research, and there was a lot about calculating what type of debris would exist, but not for just keeping it out of the stream, though.
I guess normally we want to have buffer zones and trees to shade the stream, so it's kind of a trade-off, I guess.
The Bartle did mention.
So one of the, maybe in a way pros, what that was mentioned is that the deflectors that doesn't collect a lot of debris, but then all the pictures showed a lot of debris. So how does the debris get removed? And is there a frequency that's recommended to deal with all that debris? And then if it doesn't get removed, what happens for the long term? You know, do beavers start to take that over and make now new dams that cause other flow issues?
Well, so for the deflectors, their original intent is one, to help debris by colliding with it, and then two, also just to get it off of the pier. So if it collects there or if it flows with it, as long as it's not on the pier, that's the goal of the deflectors. As for a maintenance schedule, I think that's just highly variable based on the rivers. For places as forested as here, if there was large flow events once a year, probably semi-annually, would be my guess. But that's not something that we necessarily explicitly looked at, unfortunately.
And then my question, I was looking at some of your pictures, was how does that get done? I mean, you would almost need some heavier equipment to move some of that
Yeah.
debris out of the way.
It would have to be a shovels, whatever they're called.
At one point, you mentioned that one of your papers suggested that they should be kind of in the arrowhead formation. I guess, why did you not go with that route then?
We didn't really think that the Sturgeon River was high flow, didn't have a high enough flow to necessitate that, because that would require more deflectors being placed. I think the V formations were normally for very large ones, more on the size of maybe a little smaller than the portage, with a lot of flow all the time and a steeper grade so that debris is moving faster down it.
We also have limitations with our physical model. What we recommend is to actually do a physical model of the river to test different arrays, and our model was not capable of doing it. We had a problem then.
It's very small.
We're looking at doing construction of a concrete footing in the middle of the river. How would you propose to do that?
So I have some experience with this, and the best guess that we had for that, which unfortunately there wasn't any outside consulting, was to use sandbags in a low flow season and plastic sheets and a sump pump to keep the area as water free as possible, hoping that the flow rates and the water levels would be relatively low when we chose to construct it. Any further questions?
Anybody online with a question?
Well, hello, everybody. I just wanted to quickly jump in and say,
We
this
can't
is,
hear him.
oh, you can't hear me? Can you hear me now?
Wonder how long he's been trying to ask.
Can you hear me?
Are you there?
Yeah, can you hear me now?
We can hear you, sort of.
Okay, you can relay it for me. Is that I just wanted to point out that this has been kind of a interesting experience working with the three teams and how they went about identifying the problems. And I think that didn't quite come across in it through all the different presentations. Each of these problems were, we didn't present these problems to them. They identified it based on what some of the needs in the county were around hazard mitigation and associated assessments. So I think there is something we said about that. And while some of there was the curb crew, some of the solutions may seem trivial, but they're actually quite important in terms of the impact they could have if implemented, and they continue to continue to pose a problem. So I thought that was a part of the experience of the class that didn't quite come through the presentations, but was very helpful, I believe, and in terms of what the students put together. You do see it in terms of what they have in their projects, but there was also that group work that happened. So yeah, thank you the students for working through that.
All right.
We have one more